Hello, hope you're doing great. This is Mariya Pannirrajan, your friendly software engineer. And in this video, we're going to talk about how we can implement a linked list in C++. And more specifically, we're going to talk about how we can add elements to a linked list and also how we can remove elements from a linked list. Alright, and we're going to do this in two sections in this video. Alright, so in the first section, we'll go over the theory, right, behind how what basically happens when you add an element to a linked list, the wiring that happens when you add an element to a linked list, and also we're going to see the theory, right, the theory of the wiring that happens when you remove an element from a linked list. And in the second section, we are actually going to open our VS Code code editor and code it out and see it practically implemented in code in C++, and we're going to compile it and run the application in the second section of this video. Alright, so we have a lot to cover, so without any further ado, let's get started. Let's consider this patch of ground to be your heap memory. Okay, so this is the heap memory. Just imagine that this is heap memory. So in a linked list, you start a linked list. The main thing in a linked list is basically a root node. Okay, so you have something called a root node, and from the root node is where you create this link. Okay, so for the root node, it needs a particular memory location, right? So you need a memory location for creating that root node. So let's just do that. So to when you're creating a linked list, the first thing that you would need to do is first of all create a root node. So let's just imagine that this is your root node's memory location. Okay, so you have your root node here. Okay, so let me just put even R for root, right? So this is your root node. Okay, this is your root node. Okay, so you have your memory location for your root node, and then what you would need to do, so every node, right, be it a root node or any other node, will need two things, right, in a linked list. The first thing is a value. So a root node will need a value, and the second thing, it needs a link, right, a link to point to the next node. Now let's just take these cards. Okay, I just got these playing cards, and let's consider them to be the values. Okay, so this root node is first of all going to have a value. So just to keep things simple, the first value will set it to be 1. Okay, so I have this card 1. So now this root node has a value of 1. Okay, now we have a value. The second thing we need is a link, right? A link pointing to the next node in the linked list, right? So for that, let's just make use of thread. Okay, so we have a thread here, and this thread, is also part of this node, this space. Okay, in this space that you have allocated in the heap, you have a value which is 1, and you have a link, a pointer, right? So a pointer which will help in pointing to the next node in your linked list. Now when you start creating a linked list, initially there will be only one node, right? So it will have only one node. Since it has only one node, the subsequent node, the next node, there's no next node, so it will basically be a null pointer, right? So it won't have anything to move to. So we'll basically have some kind of a null pointer somewhere in memory, and so this is basically we'll be pointing to that null space. Okay, so it doesn't have anything to point to. So this is how it starts. So you have a node that has a value and a pointer that points to the next node. Cool. Now when you add, so this is the first part, right? First feature of linked list that we are going to implement in this video. So when you want to add another value to this linked list, how will you do that? So just like how you created, first of all, allocated a space for the node in your heap memory, you need to allocate another location. So this could be anywhere. Okay, this is the beauty of linked list. Linked list doesn't need to be sequential, whereas another data structure such as an array is pretty much sequential, right? So but a linked list, each node can exist anywhere in your heap memory. So let's just allocate another location. So let me maybe okay, let's say this location, let's take this. Okay, so let's say this is the second node location that we have received. Okay, now and again this node, now this is not the root node, again this is the only root node, but now you have another node, and now this node again has two components, right? The first is the value, and the second part is a link. Now this node, let's put it a value of 2. Okay, so this node has a value of 2, and also it will have a link, right? So it will basically point to another node. Okay, so it has a pointer which can be used to point to another node. Okay, so when you create another node, first of all, what we need to do, this root node now, has to point to the second node, then only there's a link, right? So since this root node has a pointer, this pointer will make it point to the second node, right? And thereby, when you just have the root node, from that root node itself, you will get the value, and with the pointer you can reach the second node. So this is pretty cool, right? And now the second node doesn't point to anything. I mean, it has a pointer, but it doesn't have anything to point to. So now this second node will be pointing to a null pointer. Now similarly, let's create another node. So if for this, again, if you want to add another node, all you need to do is again allocate another location in your heap memory, right? So you just need another space, and in that space again, let's just put a value. Let's put the value of 3, right? So it's got a value, and yes, it will also have a pointer, right? So it's got a pointer as well, but this now won't be pointing to anything. It'll just be pointing to null, and this second node, we need to make it point to this third node. Right, so this is basically how a linked list works, right? So this is the root node, this is the king. Okay, so here, this is the root node, so this root node, from the root node itself, all you need is just the root node, and with the root node, you can just traverse through all the nodes that are in the linked list. So from here, just follow the the value and follow the pointer to get the second node, and you got the value of the second node, and from the pointer just follow the pointer to go to the third node, and you get the value of the third node as well. Cool. So this is how you add nodes to a linked list. Now the beauty of it is, so let's say now you want to add a node in the second position. Okay, so till now we've been adding nodes one after the other, like we have been adding nodes to the end of the linked list. So let's say you want to add node in the middle, you want to add a new node in the middle, okay, in the second position. So how would you do that? So traditionally, if you were using something like a sequential array, once you add a node in the middle, you would have to move all the other nodes after that by one position, because it's all sequential. Whereas here in linked list, you wouldn't have to do that, because it's just linked together by means of these links, thereby the name linked list. So over here, what we can do is, let's say you want to add another node, like node of value 5. All you need, let's say you allocate a position for it, for this new node over here, right? So this new node will have the value 5, right? And yes, it will also have a pointer, right? So it's going to have a pointer, right? So all you need to do now is just change the links, right? So from the root node, you want the second node to be this 5, right? That's it. So the first node, root node, is going to point to this 5 node. So this is going to be the second node, and this node again has a pointer, right? So set that pointer to point to the previous second node. So this becomes the third node. So easy, right? So it's computationally very inexpensive, right, to just change these pointers, and thereby now you have you literally added a new node in the second position, and other nodes just implicitly, by the nature of this data structure, they have shifted positions, right, like if you will. So you now have the root node, and from the root node, the second node now is 5, has the value of 5, and then you have the third node which has the value of 2, and then the fourth node has the value of 3. So this is pretty cool. All right, so now let's also talk about removing a node from this linked list. Okay, so removing a node again is very simple. It's very similar to the mechanism that you have used for adding a node. So let's say you want to remove the node 2. Okay, so if you just want to remove this node 2, all you need to do is you can do it in 2 ways. One is you can just traverse through this linked list and find the node that has the value of 2 and then remove it. Like we know how to traverse it, right? So we just need to start with a root node and follow through all the nodes. So we can do that. That's one way of doing it. And the other way of doing it would be if you already know the position of the node which we want to remove, right? So you can just directly traverse the linked list to reach that respective position and then remove it. Okay, so let's say this is the position 0, 1, 2, right? So this is the second position if you're starting from 0. So in that case, if you want to remove this node from this linked list, all you need to do is start traversing from the root node. Everything starts from the root node in a linked list, right? So here, from here let's say this is the 0th position. So you go to the first position, and then from the first position you go to the second position. So because of these links you can do that, right? And here this is the node that you want to remove. So what you need to, when you're traversing, you need to remember the previous position though, right? Like that's important, because so you just need to have some kind of a variable or a pointer that points to the previous position, and then you reach your current, like the position that you want to remove. Okay, so you come here, so you have pointers to the previous position and the position that you're considering to remove, right? So you have these 2 pointers, and then all you need to do is change the link. Okay, you just need a bigger wire. Let me just take a bigger string here. Make this pointer directly point to this node, right? So instead of like obviously this also would be there, right? So you can just remove this pointer to like point to null or something, and this node's pointer point to null, and you just need a pointer from here, right? From this the node in the index 1 to directly point to this 3rd node. So now what's going to happen is, so from the root node in the linked list, from here you go to the 2nd node, which is this one with the value of 5, and then from here you go to the 3rd node, which is a value of 3, because this is the this is the link. You have just bypassed, you're just not going here anymore, you're just directly going to the 3rd node, right? So this is pretty cool. And this node you can just like delete it from the heap memory. You can just like delete it off, right? And it won't be any issue, because like there's nothing pointing to that, so so that's no more. So that's basically how you remove any node from a given linked list, right? So yeah, so this is a theory behind how linked list works, especially how we add and remove items from a linked list. Now let's open VS Code and code it out and see it in action. So we have VS Code, like an empty VS Code project here. So let's just create our main.cpp file. So let's create it, main.cpp file, and let's have our main function. So main, it'll be int. We need int argument c, and we need these are just boilerplate code. Argument values. This basically returns 0, right? Yeah, 0, and perfect. So yeah, like we're gonna follow somewhat like a test-driven development methodology, right? So we're gonna follow that philosophy. We don't, like we're not gonna necessarily have a separate application called like a test executable that will run all the tests for this main application. We're just going to use this main.cpp file, like this place where we're going to have all our tests, right? So whatever we expect, we're going to write that here first, like, and then we're going to do the implementations. Okay, so you're going to make the strategy. So basically you're going to strategize first, like as in like whatever you need, just write it over here. Obviously it's going to fail, and then you need to make the failure succeed, right? So we're going to make the strategy drive the execution and not the other way around. So that's basically the philosophy of test-driven development, and that's what we're going to follow here. All right, so cool. So for our linked list was what do we need first, right? So we would need some kind of a linked list first of all, right? So linked list object, right? So this will be a raw pointer. We just use raw pointers here, just to keep it more raw and and not shy pointers at the moment. Okay, cool. So linked list, right? Linked list. So this should be, let's just call it linked list equal to new linked list. So yeah, so we just create an instance of linked list, and yeah, like when you create an instance of the linked list, right, you will need to at least have one value, right, one node in it, right? So we'll pass it in the constructor itself. So we'll make the constructor itself accept the root node's value, and the constructor will take care of creating that node. So and what's the point of, if you don't even have a root node, then what's even the point of having a linked list, right? Yeah, so cool. So this is what is needed, but obviously it's going to fail, right? So and let's just come here to the terminal, and we'll just make use of the dev toolset 7 bash so that we get access to G++ version 7, right? So this is cool. And now if we just need to do G++ main.cpp, and obviously it's going to fail because there's no such thing called linked list right now, right? So we're just using it directly. So let's just make this correct. So we just let's just correct this failure. So we just to include a linked list, and obviously there's no linked list as of now. We just need to create it. So linked list right? And yeah, so basically let's just create that file here, linked list dot header file, right? So, and in that header file, since it's a header file, we need to pragma once, and let's just make this as a class called linked list, right? And in we just have a, so right now it just needs a constructor, right? So that's all is needed. So let's just create the constructor and make it public. So public um, constructor just needs to have the same name as the class name, and it just takes in the root value, right? So it just takes a root value, and let's make use of I'm just using this handy like extension, VS Code extension called C++ definition generator. This is really useful, especially when you're working with C++ projects. So what it does is, it just like, you just press Ctrl Shift P, it'll just generate source code, source file from header file, right? So this just, this pretty handy. It just puts all these boilerplate stuff. Now and let's just make this angular brackets. I mean, like, there's no difference. I mean, like, you see, you can also use quotes here to include. By convention, I believe quotes are used for, header files that are present, that you generate, and angular brackets are used for header files that are, present inbuilt inside of like the C++ version that you're using. So let's just using angular brackets. Okay. So yeah, okay, let's just continue using whatever is coming from the, yeah, let's just continue using this quotes itself. Now here, let's just let me just slightly zoom out. Perfect. So this, we have this constructor, right? So in this constructor we will need to create a node element, right? So we need a node object, right? So node root node. As a matter of fact, the root node should be somewhat like a member variable, private member pointer, right? So we'll have a private pointer to node, which doesn't yet exist. We need to create it, called root node, right? So yeah, so that's what it is. And then that root node needs to get set up here, right? So root node, this is where you're setting it to, it's basically creating a new node. And that node, when you create it, it needs to, yeah, obviously take in the value, root value, and like, the root node won't be pointed to anything, right? Especially since this is a constructor, and here, you don't have another value, right? So it just, root node is the only node that is present at the moment. So it's going to just point to null pointer, right? So that's the next node in this linked list when you construct it, right, in the beginning. Let me just put it here. Okay, cool. So perfect. So now the thing is, we don't yet have a node, so let's just create that. So let's come here, and I'll just include node, right? So let's create node. Let's node file, and yeah, let's create that file, node.header file, right? So again, since it's a header file, let's do pragma once, and let's just make this as a struct, because it's just a data thing, right? So here it's going to be called node, and it's going to have an integer. So this is linked list of integers. Okay, so just keep it simple. So value, and like a pointer to the next node, right? So next node. Perfect, that's it. So that's all you need to have in the node. And let's just also have a constructor, to help us initialize the node. It'll take in value, and it'll take in the next node that it needs to point to. Next node. That's it. So let's make use of that extension to help us generate our source file. Yeah, cool. And this we'll make use of this initializer list. Okay, so to help us to initialize the values. So value, and we have next node is next node. Cool, that's it. So this is it. So we have our node ready. So we should, yeah, like theoretically, yeah, like we should be able to run our application without any errors right now. So let's just compile this. Yeah, okay. So linked list. Oh yeah, we need to include it in the GCC, right? So we just need to add linked list list.cpp. And what is we create? We can also create a node.cpp, right? And let's also tell g++ where you can find the header file. So just, in the same directory. Cool, no errors. Perfect. So let's just run this, and nothing will happen, because nothing is there to we're not asking it to throw anything. So let's just have a print, right? So that'll help us to validate, if our linked list is actually getting created. So linked list print, right? Obviously, this is going to throw an error if right now, yeah, because there's no, member called print. So let's just create that. So we introduce that, yeah, here. So in the public thing, we just public access modifier. So print, it's just a void print. It's not going to return anything. It's just going to print stuff. So yeah, and you can use that helper to generate that, right? So create definition, jump to it, and yeah. So here, how are we going to print all the values of the node? So what we need to do is just basically have some kind of a pointer, like call current node. So we're going to start from the root node and just traverse through all the nodes that are there and just print its value. So we'll have a pointer called current node and we'll make it point to the root node. Okay, so initially we'll be pointing to the root node, and while the current node is not equal to null pointer, if the current node is null pointer, that means we have just reached the end of the list, right? So as a matter of fact, like the previous node to the node that is pointed to, okay, it's, let's just write it out. It's better to write it out. Yeah, basically what I'm trying to say is, like, if the current node is a null pointer, that means it's already gone beyond valid nodes in the linked list, right? Because the last node in your linked list is going to have some value, right? It's going to have some value. It's not going to be a null pointer. The last node is going to point, the node that is pointed to by the last node is going to be the null pointer. So until the current node is not a null pointer, that means we are good. Those things we need to print it out. So that's basically what we're doing, right? So that's the logic. So the logic is good. So here we just need to, let's just make use of a stdc out and current node value. Let's just print out the value, and let's just have a std and let's maybe have this thing over here. Okay, see out current value. Oh, yeah. Okay, so see out won't be here, right? So we just need to include IO stream. So let's just include that hash include IO stream. See, like inbuilt header files have this angle brackets, okay, just for, okay. Cool. So we are printing it out, and then we need to move the current node, right? Like, so we are initially the root node, and we just need to move to the next node. So current node equal to current node next node, right? So that's it. So this will basically just keep moving the node across till the end, right? Perfect. So that's it. So this should just print our linked list. So let's just see if that happens. Okay, so right now we just needs to have you just have one value, right? So which is, what is the value that you want? So yeah, perfect. See, we got a value printed, and also the print, right? Let's just do something, just a cosmetic thing. Let's just have some kind of a space in between, and let's not have an endl, so that all the values of that linked list are printed in the same line. And at the end of, after it's all looped, at the end we can just have stdc out. We'll just have a new line character here, so that we have a next line character, after all the nodes, all the node values are printed. But so that's cool. Now let's try to add another value. So right, so this is cool. Let's say linked list, we want to add a value in given position. So you given a position, like a view, so when you give a value, let's say for example 2, we want to add it in the position. So this is the position 0, right? Initially, that'll be we start with 0, right, in mathematics and in computer science. So basically, like let's add 2 in position 1, okay, in the index 1. So this obviously doesn't exist. So let's compile this and see the error. Yeah, so it doesn't have that function. Let's just implement that in the header file. So let's go here again. This is it's just a void thing, and yeah, it needs the value and it needs the position. Perfect. So yeah, so this is that function, and let's implement this. So yeah, like let's just p create definition, jump to it, p create definition and jump into it. Why doesn't this not work? Maybe it requires it to be in the same line, probably. Let's see.
Okay, let's try now. Create definition and jump into. Okay, cool. So that's I think it's like a like a one small um, quirk that this particular extension has. It needs to be in a straight line. Then only it basically creates your definition for you. Okay, cool. Okay, so perfect. All right. So here, how are we going to add a value to the given in a given position, right? So first of all, we need to move to that respective position, and then we need to add it. And here, the most important node, like in order to add a new node, right, is the previous node, not even the current node. Okay. So you basically like you will be moving to the position, a given position. You basically we need to move to the node that is in this given position, but what we need is actually the previous node, so that like the new node that we create, right, needs to be pointed at by the previous node. Okay, it may make more sense. I mean, like if you look at the theory, right, where we had all these in the ground, we were drawing all these locations and having these strings that were used to point things. It make sense if you look at it once again. So like basically the previous node is very important, because like the previous node needs to point to the new node, and the new node that you create needs to point to the the current node that is there. Like, okay, it'll make more sense when we code this out as well. So first of all, we need to move we need to get that previous node, right? So we can even have a helper function to help us do that. So let's just create a helper, like a private function called get previous node of um, give node of current node in given position, right? So that's what we need. So we need to so we still need the position, and we need, so this will basically return to us a node pointer. So it basically zoom it out slightly. So this um so let's create the definition and jump to it, and then let's make it more readable. Break the lines. So here, so as you can see, get previous node of the current node in um, previous node of the current node in given position. So like yeah, that's what we need. So basically, like we give like a position, this is the current node, and but what we're interested in is getting the previous node. Okay, let's just implement that. So over here, this let's break up these lines. Okay, cool. How are we going to do that? So like basically, how are we going to move to that respect to current node and then get its previous node? So let's let's also have another private variable called size. Okay, so that will be handy for us. So it's a private variable, and initially when the constructor got constructor created a root node, the size of the linked list became 1, right? So since that's one value right now, size is 1. And like we just, when you want to add a value to a given position, first of all, it should be inside of the bounds of the size of the list, right? So as in like if you have two elements in a linked list, you should be able to add either in a new node in either the 0th position or in the first position, right? First in the 0th index or in the first index. You should not be able to add, like at least in this implementation that we're doing, we don't want to give the user the option to add a new node in like the 5th index or 10th index or 100th index when the linked list is just having two values in the first place. So first of all, what we do is we just check to see if the position is given position is lesser than the size. Okay, so initially like the size is 1, right? Like, so if you add, if you can actually add a node in either the 0th position or the first position. Okay, so those are options that you have initially, right? So if the position is lesser than the size, yes, then like it's good to go. So what we'll do is, if we'll just in order to return an error saying it's not valid, we'll just say if the position is greater than the size, we'll just say cout. As a matter of fact, we can actually put this also into a individual helper function. We'll just say boolean is given position available present in linked list. Yeah, we can just say given position present because it's understood, right? This is a linked list implementation. So is given position present. Yeah, is given position present. So int position. Let's just also create the definition and jump into it. So is given position present. So yeah, that's same check, right? So this check, we just move this over here. So if the position is greater than the size, then we return false, right? It's not present if the position is greater than the size, otherwise we return true. And also we can actually have some kind of a print statement here saying that given position is not present in linked list. stdndl. Cool. So that's it. So this we can use it over here when we add a value to in the given position. First of all, we can just check, right? If you know is given post, if the, we'll just check for the position if it's a valid position in the first place. If it is if is given position present, if it's not present, not here, then we return. Yeah, that's it. We just return. We don't do anything. We can't add anything, right? So we just return. Anyway, that that message also will come to all the terminal. So that's cool. So we can actually put this in this single line as matter of fact. Yeah, that's it. So and in C++, if if it's just a single line statement after it, right? You don't even need to have put this curly bracket on. Okay, so that's a nice feature. All right, so we just return if the position is not even valid. Otherwise, what we do is we just have a pointer called a variable called current position, and we'll set it to 0 because initially it will be 0, and we can use that to loop. So if the current position is not equal to, until it's not equal to the given position, we loop through it, right? So and along with this we also need that node, right? We need the root node. So we will say current node equal to root node, right? And we can just so initially it's root node, and so you just move the root current node. So current node, this is how you traverse through the nodes, right? It's next node, current node equal to next node, right? So you just keep on traversing through it, and also you need to increment the current position, right? So just position. So so that's how you just go through each of the positions, and if the position is equal to a position that you're interested in, then it'll just come out of the loop and you'll have that respect to node, right? So perfect. There are certain possibilities that are there now. So primarily there are three main things we need to consider. So let's say if the oh, this actually I believe we need to do it inside of that node where we get the previous node. So that's where we are need to traverse, right? So that's where we need this needs to be. So it should not be inside of directly add value in given node. Because we can actually move this into a separate function, because anyway we'll need the same functionality of getting the previous node of a current node in given position for the when we actually implement our remove value in given position as well. So just to keep avoid duplicating code, right? We'll just keep move it into a separate functionality because it's more succinct. So yeah, so get previous node of current node. So here, right, like so you get the position, you have the position, and yeah, so and yeah, the current node, we just created a variable current node and it's pointing to the root node, and yeah, we're just moving through each of the nodes, and if the position matches, right, if the index matches, so then basically we can just we know that we have got the current the node that is interesting, that node that we need of for us. Now what we need to do is but the thing that we want to return is the previous node, right? So even before moving to the next node, we need to first of all have another pointer here, which is the previous node. Now the previous node initially will be null pointer, right? For the first node, there is no previous node. So it's just the root node alone, right? So in that case, the previous node will be a null pointer. So if in case the user wants to add a node in the 0th index, in the 0th position, so that means what's going to happen, it won't even go inside the loop because the current position is 0, and like the position that if the user had given was also 0, it won't even go inside the loop and it'll just come outside here, right? So in that case, if the current node, if it is or rather you can even check the previous node. If the previous node is null pointer, that means it didn't even go into the loop. It's just the first character that we are in, first node that we have here, right? The current node is right now the first node. So if the previous node is null pointer, so that means we are dealing with the first node. Okay, so there's no, we have, so that's the scenario where you will have a, see, if the previous node is in the null pointer, so that means you're dealing with a root node. Okay, so you're always dealing with a root node. So that means what we need to do is so we need to create a new node element, new root node equal to new node, right? So it'll have taken the value, and this will point to the root node, the existing root node, right? So that's what it needs to do. So we have a new root node. Okay, the new root node that we created is here, the new root node, and that new root node should point to the old root node. That's what is happening here. So okay, it doesn't have a value here, right? Oh, cool. Okay. So this needs to, the actual addition and all needs to happen in the over here in add value in the position. Let's comment it out. As a matter of fact, let me just move things just to make it more cleaner. So here, these are helper functions. You get node, previous node. Actually, these are private. As a matter of fact, these are also private functions. Let me just put these double underscore. So this get previous node of current node in given position, and this given node, these are all both private stuff. So let me just I just made them private. I just need to add it to underscores. So let's cut this and move it above. Okay, just to, it's not necessary to keep it up. It's just cosmetic thing I like to do. Anyway, so here add value to, so here first of all we have just checked if the given position is valid. It's actually present inside of the linked list, and then we need to get the previous node. Then only we can actually add a new node to the previous node, right? Make the previous node point to the new node and the new node point to the current node. So we would need to get previous node of current node in given position. So we just give the position, and this will be our previous node. So previous node equal to, right? So basically this will give us a previous node, and with the previous node, so there is a scenario where this previous node might be a null pointer as well. That's also fine. So if it's a null pointer, that means what does it mean? We are in the first node. So that's what it means. Okay, so we need to handle that a bit differently. So if the previous node is a null pointer, so that means the current pointer is the first root node, like the old root node. So that in that case, let's just create a new root node. Right? So we have created a new root node and made that node point to the old root node, right? So that's what we have done. And then we just need to update our root node to be the new root node. Hope it makes sense. Yeah, so like we have a new root node. So basically what we have this diagram here, right? So basically we created a new node and made it point to the old root node, and then this is now the new root node. That's it. So that's what we have done. Perfect, cool. So now with this, right, so what will happen, with this code, we should be able to add nodes on the left side, as in we should be able to add a node in the index, 0th index. We can just keep on adding more and more nodes. So let's just see if that works. Okay, so initially the value would be 1, and then with this, right, it should be 2 1, right? Because we are adding things on the left side. We are adding things, we are basically adding a new root node. Okay, let's just see if that happens. Instead of so initially one was root node. Now 2 would, the root node should have the value of 2. So yeah, let's see. Compile and run. Yeah, see, as expected. So initially 1 was a root node and that was only node, and then we added 2. Now 2 is a root node, and then you have 1. The old root node is now moved to the right side. As a matter of fact, you can just keep on doing this. So you can actually add make another node called 3 and make that as a root node. So now 3 will be the root node. See, and you have 2 and 1. So this is pretty cool. So you can just keep on adding more nodes and on the root side of things, on the left side. So that's cool. Now let's that's nice, but this will fail if we if we, instead of in the root side, let's say there's already a node in 0th index, right? So if we try to add another node in index 1, I don't think it'll do anything as a what will even do. So I mean, we have not written code for that logic right now, right? So it'll just it won't do anything. So it won't know how to insert a node if a new index has been given. Okay, so let's just handle that. Let's just write the code for that. So so previous node, okay, is null pointer, means fine if that means the first node. So otherwise, if it's not the previous node, what should we do? So if it's not the previous node, all we need to do is previous node dot next node equal to, okay, so now we have a previous node. That means we can just create a new node and have it put it okay, give a value, and this new node should be pointing to the current node. So how do we get the current node? So we just need to say no node, the current node equal to previous node's next node. The previous node's next node is the current node, right? So that's how you get it. So previous node, so current node, and the previous node next node is equal to, so we are changing it, right? So we just have a we're storing the current node, which is the previous node next node, and then we are changing the previous node next node, which is the current. We're changing the current node to be the new node, right? So this is with the new value, and then that new node needs to now point to the current node, right? So cool. So let's just see if this works. so yeah, like see, now instead of 0, instead of adding it in the root level, in the first index, we're trying to add it in the like the first position, okay, 0 1, like the second, basically the second position, first index, which is the second position. So let's just see if it works. So let's just compile this and run. It's a seg fault. Okay, why is it doing a seg fault? Okay, let's just figure out, let's just find out where it's actually doing the seg fault. Okay, so let me just is it doing a seg fault in the print? Let's just check that. Yeah, it's not doing it in the print, it's actually doing it over here. Okay, let's just see where it is actually doing the seg fault. So I'm pretty sure it's not doing it here, right? Because it was fine there. So let's just do a print statement here. We'll just call test 1 and test 2, test 3. So let's just see where it is actually crashing. Test 1 after test 1. Okay, so this is where it's crashing. Previous node, why not? We know for sure that if previous node is a null pointer, so if previous node is, so here when it comes, it's not a null pointer, right? So if it's not a null pointer, we should be able to get the next node of it, right? Get previous node of current node in given position. Let's go here. What are we returning? We're not even oh gosh, we're not even returning anything. Okay, that's okay, my bad. So here first of all, yeah, like we are not even previous node is equal to current node. Yeah, so we need, this should be the current node, and then only we change the current node, right, to be the next node. So and finally after you loop everything, we just need to return the previous node. Perfect. This is good. Now we are actually returning something, and so this will work. Okay, so this will definitely work now. It should work. Let's see. Okay, let's compile this and run. Okay, 1 and this print this out. So it should print 1 2. Okay, So we already have one, so the 2 should be now added in the second place. Yes, see, it works. And the other thing also works. If you put 0, it will add 2 in the beginning of the linked list. Yes, perfect. This is awesome. So now I think we can actually add how many elements we want. Like let's add 3, and like let's see if this works. Okay, given position is not present in the link. Okay, I think we missed one point. So which was, we need to increment the size of our linked list, right? So we had implemented it initially in the constructor, right? We need to do the same when we add a new element to the linked list as well. So add value in given position. Yeah, so in this function also, at the end, after we add an element to the linked list, we just need to increment the size. That's it. Now it will work. Let's just compile this and run. Yeah, perfect. See, 1 2 3, perfect. So you can just keep on adding how many ever elements you want into this linked list. So let's just add 4 in position 3, and we'll add 5 in position 4. Okay, so let's just see. Perfect. See, 1 1 2 1 2 3 1 2 3 4 1 2 3 4 5. Perfect. Cool. Now the cool thing about this add, right? You can add new values at any any place in this linked list, right? So if, let's say for example, we want to add the number 7 in the second position. Okay, so if you want to do that, all you need to do is just mention that, right? So here we'll add the value 7 in the 0 1, which is the second position, right? So if we do that, everything will just work. See, second is 7 is now added in the second position. So everything else, it just in memory it did not get offset. Okay, the memory is still the same place. It's just the links are changed to accommodate this structure. So that's the beauty of it. In memory we did not offset anything, and now it's not, this is not an expensive operation. Yes, like the traversal, yes, it's an O of n operation, but still we just need to change the links, and it just, you can insert. So let's say if you want to insert a number and then number 7 0 1 2 3 in the third place. Okay, so let's just do that also quickly. So if you want to insert 7 in the third index position, cool. See, 0 1 2 3, see? And the remaining things just slightly move. This is so perfect, right? This is so cool. Nice. So this is the adding part of it, right? Now let me even put a nice print statement in the beginning to signify that we're adding elements. Adding elements. We would need IOString, right? Include adding elements to linked, and we'll now do removing elements from the linked list. Session elements from linked list. All right, now let's write the code for removing elements from the linked list, right? So for that, let's just assume that it is already there, as we always do, and let's do linked list remove element. Just copy the same, remove value in given position. Instead of add, we just want to remove, and we want just the position, right? So here let's try to remove these these two 7s in the position 0 1 and in position 0 1 2 3, right? In 0 1 first. So 0 1, so in position 1 we want to remove this 7. Now obviously it will not work, it's going to throw an error. Let's make it throw an error first, and let's fix it. So the print is still there. So perfect. So if we just compile it now, and it's going to throw an error saying that this thing is not there. So let's just fix it. So here let's add this, which is also going to be a void function, and you have the position, right? And cool. And let's go here. Yeah, let's just use the tool, right? So just use create definition and jump into it. And so yeah, like here again, when you are removing, right, first of all you need to check if the it's a valid position, right? Now, as a matter of fact, yeah, like we need to have a check here, right, which is basically saying if position is, you know, if the position, actually we can use that, if the position is, it should be inside of the size, right? So you should be able to, you know, only be able to remove things that are already there, right? So if you should not be given a position like 100 or 50 or, you know, some absurd number which is not present in the linked list. So for that we already have this check, right, which is given position present. So if the position is present only, then we can remove it, right? So if it is not present position, then we return, right? We don't, you know, do anything, right? So we obviously will get that message and also, so that's cool. So let's just first of all do that. We'll just give a absurd number like 100 or something, which we obviously know it's not present in this like this. So in that case, it should give us this message saying that, you know, it is not, you know, the given position is not present in the linked list. So it's exactly the same value. It's not, nothing's changed. So that's cool. And but if we actually give some value that is valid, so that is which is basically 1, for example, which is a place where 7 is present, so in this case it should work, right? So and there's another scenario where it should work, and there is also another corner case that, you know, we need to think of, right? If all the elements are removed also, it should not, it should just say, you know, there's nothing to remove. So that's something we need to just keep in mind and implement data. But for now we just implement, like, so if it's a valid number, that, you know, then some kind of implementation should happen, right? Or we just quickly say, you know, implement that corner case also, or we'll do later, based on, we'll do this test driven development. I mean, I'm just forcing myself to, you know, not add more features than, you know, we are writing test for. So okay, cool. So we'll just say, um, if it's a, you know, if the position is not present, then we just return. Otherwise, we would need to remove it. Okay, how are we going to do that? So first of all, we need to go to the previous node, right? So that function that we have, so we just we'll get that, you know, previous node of the node in the given position. So node previous yes node equal to, it's a private function get previous node of the current node in the given position. So position is position, so this will give you the previous node, and if the previous node is null pointer, so that means it's the first node that we are dealing with, just like how we did it earlier. So in this case, if it's the first node, what we need to do is, so we just need to store the old root node over here, old root node equal to root node, yeah, and then we just set root node to be equal to old root node's next node, right? And we delete old root node, yeah. Now one thing that we need to be careful here is, like, we don't want to, we should not delete the root node if that's the only node that is present in the linked list, because, you know, that's, you know, that defeats the entire purpose of having linked list, right? If you do, if you know, at least in this implementation, we will not allow people to do that. Like, there is, yeah, technically you can actually delete the root node also, and then, you know, give another function to set, you know, the root node, and, you know, so that's still a possibility. But we, in this implementation, we just restrict the user from deleting the root node if there's only one node present. Okay, so so here what we'll do is, if um you know, like, we will say if the size is 1, right? If size equal to 1, right? 0, yeah, so 1, if the size is 1, we don't allow to, you know, we just say cannot delete root node when the size of linked list is size of linked list is 1. Cool. So, and then we just return. We won't allow people to do this if the size is 1. Right. So we then, when we come here, we know for sure that the size is not 1, so we can, safely delete the root node. Okay. So we just, stored the old root node in this pointer, and then, we just set our root node, the new root node, to be the next node of the old root node, and then we just deleted the old root node. So that's basically what we've done. So this is a scenario we are doing for the first node, right? So otherwise, if it's not the first node, then it's pretty straightforward, right? We can just make the previous node next node. First of all, you need the current node, so let's get the current node. Current node equal to previous node's next node, right? And then we just need to make the previous node's next node point to the current node's next node. Next node, right? And then finally we just need to delete the current node, because there's nothing pointing to the current node anymore, right? Previous node's next node is pointing to the current node's next node, and the current node we just delete it. That's it. So that's pretty much it, and this should delete our nodes, remove our nodes. So let's see if this works. So yeah, this obviously works because it's an absurd number and it just says that value is not present, that index is not position, doesn't present. But now let's see if the number 7 gets removed from the index position 1, right? Let's just see that. Compile, run. Yes, it does. That's pretty cool, right? See, the 7 got removed, and let's try to remove more numbers. Let's remove the value that is present in 0, 1, 2 in the second index, right? It should also, that should remove the other 7 as well, right? Yes, it does. Now what we'll do is we just keep deleting everything, and let's just make sure that everything gets removed, and even when everything gets removed, it just tells us that you can't delete anymore. That's an important scenario as well, right? So if there's only one item in the linked list, we should not allow people to delete. We have already wrote the code for that, right? If the size is 1, we don't allow people to delete anymore, right? So let's just see if that also works. So we can just quickly delete everything. So from in index 0 itself, we just keep deleting everything, right? So index 0, whichever index you can just choose and delete 1, 2, 3, 4, 5. So five elements, right? We'll just delete 5 times. 1, 2, 3, 4, 5. So okay, so let's just see if this also is good. Perfect, right? So cool. So till 5, it's there. So let's just see if we do it once again. Let's see if we get that message. Oh, seg fault. Okay, why? So it's already over here. Are we yeah, we're not subtracting the size, right? So that's another, yeah, that's important too. Okay, so every time you remove a value, right, at the end we need to decrement the size, then only the size counter will work, right? Yeah, so then now it should work. So let's just perfect. See, it's deleting everything, and then finally it says length size is 1, so it can't delete. Yeah, perfect, cool. That's it. So this is the implementation of linked list for adding elements in given position, and also for removing elements in the given respective positions.
So yes, hope this video on how we can add and remove elements from a linked list was useful. Thank you so much for watching, and I will see you again in another video. Cheers!